Chemical kinetics. Let me pin my video, be sure everything's in line. Yeah. Okay. This exam is only going to have one chapter on it, chemical kinetics. And it's probably a good idea to do that because kinetics tends to give students the heebie-jeebies. We'll focus on this one topic, and we're going to cover kinetics as a measure of reaction rates and develop some techniques for quantifying those rates. And then once we once we get a handle on kinetics, we'll be able to talk more intelligently about equilibrium. So I'm going to share. Come on. Looks like it's still recording. Yeah. Okay. We share the slides here. And hope our internet connection holds. There we go. Now let's make a slideshow out of it. Come on. Try it again. There we go. All right. So, like I said, chemical kinetics is study of reaction rates. And in its most basic form, we're describing the change in concentration of any component in a reaction versus the amount of time it takes to make that change. So that's why the rate is basically expressed as a change in concentration of some reactant or product. At this time, it doesn't matter, over a certain period of time. I have some noisy neighbors. I think I'll go close the door. Okay, back to the topic. Now I lost my inset. Where is it? Where did it go? No, that's not it. Screen sharing. Okay. Oh, there it is. There. Okay. All right. So remember, typically what we do is we say this would be in terms of the concentration of A at the final concentration of A minus the initial concentration of A. And this would be the final time minus the initial time. Okay. So that way, if we're looking at a change in A as a reactant, then the final is going to be less than the initial. That'll make it a negative number, and the rate will be negative because the reactant's disappearing. And typically, especially when we use square brackets, we mean molarity. That's what square brackets mean. And it'll mean that the same thing when we start talking about equilibrium in the next chapter. Square brackets refer to molarity. Okay, here's a set of data. And what we're looking at is for this reaction where we have NO2, and these are all gases. This one reactant decomposes into two products. So you'll notice that as we're watching it over time, and in the beginning, at time 0, when we first start, we have NO2, but we don't have any products. This is known as initial conditions, and any changes that occur at this instant or very short period of time after that instant, this is known as an initial rate. And the advantage to using initial rates is that the return reaction has no impact on the forward reaction. That's one thing that we'll pick up again in equilibrium. Whenever you've got a reaction set up, there's always the possibility that these reactants can do their thing and end up as reactants again. These products can become reactants. So you got both reactions possible. So when we study the reaction, we try to, we don't always have to do this, but we try to look at it as initial rates. There's still information that can be gained from watching the reaction all the way through till whenever. But that's one of the options. Notice that the concentration of NO2 in the first time interval has decreased by 0.0021. So the change there in NO2 is a decrease of 0.0021 molar. Notice also that the NO has increased. I shouldn't say the rate. That's not right. It's not the concentration. Well, yeah, that's right. The concentration, concentration has changed for NO2. I don't have a time factor in this one. This is just the change that's occurred. And since these are 1-to-1, 2-to-2, or 1-to-1, then you should also see an increase in NO equal to a positive 0.0021 in that same time interval. And that's what we see. Also, this one is actually 1-to-2 or half. So the change in O2 is equal to an increase of 0.0011, rounded off. And those changes that occur through this entire data set follow that stoichiometry, 2, 2, and 1. Now, the difference, the first time interval has a change of 0.0021, but the second interval only has a change of 0.0014, right? So it's not the same change in the second time interval. Our rate is changing as time proceeds. And this kind of hard to see, but this line right here is the NO2, the reactant. And notice it starts off here, and the products start off down here at nothing. So gradually, we decrease the reactant and increase the products. And notice that the oxygen increases at a slower rate than NO does. Now, in graphical, calculus terms, what's happening on that curve as an expression of the rates not the same all the way through the reaction. We'll see the reaction change like that. Then the reaction rate is actually the slope of the line at any point, the tangent to the curve at any point. So the slope is changing. That's what's called the instantaneous rate. So at any one point along here where you have a tangent, you can draw a tangent straight line on that curve. That's the instantaneous rate at that particular time. So if we have time on this scale and concentration over here, then the instantaneous rate is changing. So for any reaction, we can express the rate of the reaction in terms of what's called a rate law. It shows how the rate of the reaction depends upon the concentration of the reactants at any time. And that's actually an expression of the instantaneous rate. Because notice that that particular expression, rate equals, well, let me draw it. Let me write it up here first so before I start talking about it. The rate law says the rate, whatever it happens to be, there's a constant times the concentration of, in this case, it's NO2. We'll use theirs, to some power. And that power is known as the order for that reactant or product. The order for that term is the power of the concentration term. And that is a constant if the temperature doesn't change. As long as the temperature is constant, then this K is constant. If we change the temperature, the K changes. So this rate law is for, in this case, we only have one term in it because there's only one reactant. And that's typically what we do is watch the disappearance of the reactant. It's just more convenient that way. Okay. So for that particular reaction, this is the rate law. And what we want to do to express this is find out what that power is, the order of that reactant, and the K value. So that's our ultimate objective. Well, yeah, that's another good reason. That statement is we study the disappearance of the reactant because we typically watch the concentrations at the very beginning of the reaction, the initial rate. It's important to remember that this value right here is not derived from the balanced chemical equation, the overall equation. Right? The order of that reactant has to be experimentally determined. Now later on, we're going to see where if we can, I erased the equation now. If we do that and this, then this is the overall equation. This is what you start with, this is what you end up with. But we know that there's a lot of stuff going on inside that arrow. And we're going to get at that in a few more slides. When we talk about reaction mechanisms, there are stepwise changes that occur here to get from there to there. And when we look at those elementary steps in this process, then we can use the balanced elementary steps to say something about that value for each one of those steps. Right? But for the overall equation, that value must be experimentally determined. And actually that's an advantage, because if we determine this value by one method, and then we propose elementary steps in here and deduce that overall value from these elementary steps, they should agree. If they don't agree, then that's an indication that our elementary steps are wrong. More about that later. Okay. So we can express the rate law in two different ways, and they're both joined at the hip. You can derive one from the other. This particular arrangement is called the differential rate law, or just the rate law. And it only shows how the rate changes with concentrations of the reactants. The integrated rate law, however, incorporates a change in concentration versus time. It includes factors in here that include time. The integrated rate law, sometimes that's more useful, actually. So we're going to go through several types of rate laws in just a minute, and relate them each to their rate laws to the integrated rate laws for each type. Okay, this is just a summary. The first statement just reinforces the idea that we are going to study the reactions under conditions where the reverse reaction is insignificant. And then, since the differential rate law and the integrated rate law are well defined and related to one another, all we have to do is determine one, and we can infer the other by mathematical means. And which one you use is determined by convenience, experimental convenience. Some are easier to get at than others. Once we know the rate law, the overall rate law has been experimentally determined, that helps us tease out possible individual elementary rate steps, the stuff that's going on in here. We'll talk about that in more detail in a few minutes. Let's see. There is actually a method of initial rates that's used to determine the order of each one and the rate constant. And it's also useful for rate expressions that have more than one term. So you have three reactants and produces some products. Then you may have a reactant A and a reactant B and a reactant C, and each one will have a different power. Well, they could have the same powers, it doesn't matter, but they have to each be individually determined. This method of initial rates, which we'll do example at some point in this discussion. Okay, so if we have an expression where there are two reactants that are involved, we'll use a generic for this one. Then if the reaction is, say, A plus B yields something, then we'll have a term for A, and they use an N for that order. And this one is B, and we use an M for that order. Well, the reactant orders are the powers of the terms. So the order of this reactant is N, the order of this reactant is M, but the overall order is N plus M. That's all that means. There's nothing magical about it. So let's just reinforce the fact that
The question is, how do exponents, these orders in the rate law, compare to coefficients in the balanced equation? They don't. They're not related at all, as far as we're concerned at this point. Primarily because they're not related, because the balanced chemical equation is an expression of stoichiometry. How much of this yields how much of that? It doesn't matter how fast it happens. This is an equilibrium process that we're talking about. Whereas the rate expression with its powers is talking about how fast you get from one point to the other. So they're not related at all, except for this note at the bottom. Once we get at the elementary rate law steps, then we can say something about the orders in terms of the elementary steps. And we'll work, I hope we have time. Yeah, I'm sure we will have time to work one or two of those problems. All right. Now, I mentioned different types of equations, different orders. So if we're focusing on one reactant, then we can use whole numbers. And for this first one, the zero order, the order of A is 0, which makes it mathematically 1. So that means that the rate is actually equal to the constant. And what that means is the concentration of A has no impact whatsoever on the rate constant. Okay, so let's put 0 order over here. Now, I will say, as a caveat, when you actually do these experiments, and the one we're going to do next week will probably bear me out. When you do these experiments and determine the order of each reactant in the process, and our experiment's going to have 2 reactants, right? And I'll talk about how we get around that in just a minute. But this is an ideal situation where you have the order is a whole number. When you actually calculate some of these orders, they may come out as fractional numbers. Okay, so this is the ideal situation where the order is a whole number power. So this is where we're starting. 0 order. So in this case, the rate law says the rate equals some k times A to the 0 power, which is equal to k. And this is, and that's the differential rate law. The integrated rate law is you have the raw data and you plot the raw data against time. So if that's the case, then at any one time t, we can calculate the concentration of A if we know the K value, how much time has elapsed, and the initial concentration of A. Right. So in this one, you do want to know the values of A. And notice what we have here. This is like Y equals MX plus B. It's a straight line. So if you plot the data, if you plot the raw data here against time, right, you'll get a negative, yes, you get a negative value in a straight line. So if your reaction order is 0, and you plot the raw data like that, A against time, you'll get a straight line, right? If it's not 0 order, then you'll get a curve of some kind. There's one other thing that we can determine here, and that's, well, there's a plot. So that's what it would look like. And this negative K is the slope on that line, right? Slope. Excuse me. We can also determine the half-life. And the half-life, it's similar to radioactive decay, right? That's where I first heard of half-lives before I heard it for chemistry. But the half-life of the reaction is you start off with some value for A, and it might be the initial one, right, when you first start off, or it could be at any point during the experiment. And how long does it take to lose half of that value? And you need to know both the initial concentration and the K value. And you can calculate the half-life, or you can use the half-life to determine one of these other factors. If you know the half-life and you know this value, you can find out K from there. So this formula could be useful. Once you've determined its zero order, then you can use it. Okay, you can't just plug numbers into it and expect the right answer. Okay, let's see. Do I have the? No, I don't. Excuse me. I'm just flipping through to see if I've got. No, I didn't. In my New River set of slides, I have incorporated a slide that actually derives this value from there, but it's not something you need to know to pass the course. It's just interesting information for anyone who's really immersed in the math of the whole thing. So the next one we have is first order. And this is just what it says. The rate is equal to some K times A to the first order. Okay. Let's see. There it is. That's the, and we usually don't write the one up there. The differential rate law is that. The integrated rate law uses the natural log transformation of these values. So the natural log of A equals a negative K times T plus the natural log of the initial A. Okay. So what that means is if you take this data set, say it doesn't give you a straight line, right? Take the data set and take the natural log of all the factors, right? You'll have time, and then you have concentration of A, and then you can have a log of A, right? And you just have values over here and values over here that match up like that. And if you plot time against the natural log of A, then what you should get is another straight line where the slope equals minus K. See, y equals mx plus b. And this one has a half-life expression also, which is on the next slide, I think. Well, we're going to look at this first. In this case, the decomposition of dinitrogen pentoxide over time, excuse me, gives you a negative slope. So this one is a first order rate function for decomposition of N2O5. The half-life for the first order, T1/2 equals 0.693, I believe it was, divided by K. So notice the difference between the two. This one depends on the initial value of A, if it's zero order. If it's first order, the half-life does not depend upon the concentration of A at all. It only depends on the K value. All right. Okay, so we got a little problem here. Let me check my hard copy, see if I need to put any of this on the board. If I don't, then that'll save us a little time. Good. No, I've got an animated slide here. It's gonna go through this problem. So a first order reaction is 35% complete at the end of 55 minutes. So I'll build a little table up here. So if we got a first order equation, so it's like this one, first order. And then what it says is after 55 minutes, so there's your time in minutes. After 55 minutes, you've gone from some value here and reduced this value by 35%. So if you reduce the value here by 35%, what's left? 65% is left. 0.65 of the initial concentration is left over, right? If it's 35% complete, it's moved that far down to 0.65 of its original value. Okay. So we're also told, well, I've covered this already. It's a first order equation. So we would start off with this value right here, this integrated rate law, right? What we want to do is ratio the current value. This is now equal to that. And ratio this one to that one, because the ratio is 0.65, right? If we take this one now and put it on the other side, right? Our current value divided by our initial value is 0.65. So that's what this first block does. It takes that equation and reduces it to this ratio of A to A0. Now at this point we've come from rearrange the equation. Now we've got log A minus log A0 equals minus KT. But remember, the rules of logarithms are if you take log of A and subtract log of B, then that's the same thing as log of A divided by B. So that's what we've done here. We've used that rule from the logarithms to say this expression is the same as that expression. And then we want to convert that to where we have this expression without the log. You don't want the log in there. So what we've done is we've used the definition of logarithms, right? In this case, log base E, of course, of X equals Y. So what that means is X is actually equal to E to the Y power. So that's what we've done. We got rid of this log by saying this expression says that ratio there is equal to E to this power. That's how far we've gone so far. Now we've got an expression where we can substitute 0.65 into that ratio. And that should be the next part of this operation. Okay. There we go. After 55 minutes, the ratio of A to A0 is 0.65. And now if we plug that value in to is 0.65 is equal to E to the minus K times 55, because 55 is the T value. And now our unknown is K. So now we've got to solve for K. And the way you do it is you say this expression right here. Let's see. Oops, sorry. This expression right here, if we take the log of both sides, the natural log of both sides, now that's the natural log of 0.65 equals the natural log of E to the minus K 55. Okay, but the log of E to the to any power power X, since this is the base, is the same as X. And it works with any kind of logarithm. I mean, if we used common logs like that, if we had common log and 10 to some power, then that would be equal to the power of 10. So that's all we've done. But now we have the log of, let me get rid of this. Now we have the log of 0.65 is equal to minus k times 55, and we just solve for k. And k turns out to be 7.8 times 10 to the minus 3 reciprocal minutes. All right, so now we know what the k is. Does it want to know anything else? No, I just wanted to know what k was. Okay, now we can go to the second order. And this is the last one we're going to look at. And remember, when we're talking about orders in these terms, we're only talking about one reactant. Just one reactant for each one. Got to keep it simple in the beginning. So for second order, we have rate equals k times a squared. Excuse me. And the integrated rate law, rather than natural log or raw data, we have the reciprocal of. The reciprocal of log equals k times t plus 1 over the initial a. So if you're given a set of raw data and you will say which one of these is the proper order for that reactant, you just set yourself up a table with time here, the a value here, and then you go natural log of a, and then you do reciprocal of a. And if you use Excel spreadsheets, it's simple. You just plug it in and do the function, natural log function for this column, reciprocal for that column, and you just go bam, and there's all your data. And if you're familiar with how to graph with Excel, then you can set up, they call them charts. You can chart the data and see which one is the straight line. But in this case, with the second order, when you plot the reciprocal of A, it gives you a straight line, but it's a positive slope. See, that's positive. Here's an example where you have the decomposition of, let's see, that should be C4. I'm not sure what that is. That's a hydrocarbon of some kind, but it's unsaturated. That's neither here nor there. But notice if you take the natural log of that one, you still get a curve. But if you do the reciprocal, you get a straight line. Right, so now the slope of the line, in this case, is actually equal to k. And then, of course, we have a half-life. So what's the half-life? It's on the next slide, I hope. Yeah. It's simply 1 over k times the initial value, initial concentration. Okay. What this says is, as the reaction proceeds, the concentration of A is inversely proportional to the half-life. So what that means is, as the value of A decreases, then the half-life increases. It takes longer and longer to cut the value in half. All right. Oh, one other thing. Notice that for these half-lives, where's the K? The K is in the denominator for every one. which means that the half-life is also inversely proportional to the K. So if your K changes, say you change the temperature, and the K changes. If the K gets bigger, then the half-life gets smaller. Just wanted to point that out. Okay, I'm going to leave that there unless I need the space. For this reaction, we have the coefficient of A times big A yields some products. And if we say that the initial concentration of A is 5 molar, and the first two half-lives are 25 and 50 minutes, then we want to write the rate law for this reaction and calculate K, and then determine how much is left over. Once we determine what the rate law is, how much is left over after 525 minutes. Now, I think I have this one on the slides also. Let's see. Well, yes, but I think it'll make more sense. I've got some of it in slides, but I think it'll make more sense if I might have to erase some of this. Well, let me see. Let me take out this graph and this much. See if I can put it over here in this corner. So what are we given? We're given concentration of A and half-lives. So if we look at A here, and the initial concentration of A, excuse me, this is time through the reaction. There we go. The initial concentration of A is 5 molar. Okay, that's at time 0. Now, after one half-life, 25 minutes have elapsed. So at one half-life, how much of this is left? Well, half of it. Okay. After the second half-life, that means we've shifted this now to the initial concentration for the second half-life. So the second half-life takes 50 minutes. But what's the time in the reaction? It's actually 75 minutes. And the value here is half again, 1.25 molar. Okay, so that puts our data up here for us. And the next thing we have to do is determine, is this a 0, first, or second order reaction in order to write the rate law, and then use what information we have to calculate the K. And I think that's on the slides. Let me see if that's on the slides. All right. Notice, first of all, that the half-life depends on the concentration. The concentration is different here than it was there. The first half-life is 25 minutes. With the changing concentration, we get a different half-life, right? 50 minutes instead of 25. That means that it cannot be first order, right? Because the half-lives are dependent on concentration. Well, actually, the half-life's dependent on concentration over here too. But let's say, for argument's sake, that we've eliminated, excuse me, my mistake. The half-life is dependent on concentration, whereas this one is not. So that means first order is out. Can't use first order because there's no dependence on concentration. Okay. So it's either 0 order or second order. That simplifies things a little bit. Now, if the rate law were 0 order, then half-life would be equal to initial value divided by 2 over K. All right. So in the first case, after 25 minutes, 25 minutes is the half-life. And the initial concentration is 5 divided by 2K. So that's what this first equation shows right here. Right? 25 half-life, 5 concentration, solve for K is 0.1. Then we do the second half-life, 50 minutes. And the initial concentration now is 2.5 because we're starting from a different concentration. Then we solve for K and find it's 0.025. Can't be. That's a constant. Our constant is changing, right? It can't do that. So that means zero order is out. That means probably second order, but we want to confirm it. So if it's second order, we do the same type of calculations. In this case, we substitute for the first one in the values here, right there, and solve for K. And it's 1 divided by 125, and do it again for the second step. It's the same number. Right? So we have a second order equation. Right? We determined that this reaction is second order in A. So if we write the rate law, the rate is K times A to the second power. All right. So what's K? Well, let's see. How'd they get that? Oh, we can use this equation right here and plug in the initial value of 5. K is an unknown. We could either go this time interval or we can go all the way down. Right? This will be initial, this will be final. So it'd be 5 here. And this would be 1.25. And the time elapsed is 75 minutes. And then solve for K. And if we do that, then our K value is 8 times 10 to the minus third. All right. Now, how do we calculate A after 25 minutes? Well, now that we know what K is, we can plug in K. What was it? 8 times 10 to the minus third. We can plug in 8 times 10 to the minus 3, and we plug in 525 minutes, as long as it's in the same units, time units here, and it is. Then we can plug in initial value is 5, and the unknown is this one. What's the final value? And solve for that value. If we do that, oh, there it is. Okay. If we do that, then we find that the final value after 525 minutes with that K and that order reaction, the value is 0.23 molar. So over that amount of time, we've gone from 5 to 0.23 molar with that mechanism, that rate law. There it is on one slide. All right. So this is just a refresher. How can you tell the difference among first, second, and zero, first, and second order rate laws from their graphs? Right. You just say, oh, I guess I have to answer that one. You do, like I said before, you set up your table with time, raw concentrations, natural log of the concentrations, inverse of the concentrations, and then plot each one, time against the other, and time against the third one, and see which one is straight line. And if you use Excel to do that, it shouldn't take much time at all. So what do you do if the rate equation is dependent on the concentration of 2 reactants? Right? In this case, we were only looking at one reactant and what is its order. But if you have two reactants, right, you've got two things going on at once. So if the concentrations of both of them, let's say you have two reactants, A and B, right? And the rate law then would be what? Equals some K value times the concentration of A to the N times B to the M. If the concentrations that you start with are low enough so that they're both changing at the same time, it's difficult to tell, right, to deduce what type of graph you're going to get. So here's what we do. Here we go. You increase the initial concentration of one of them. We're going to say B. Increase the concentration of B to such a high level that it effectively does not change during the reaction. And since we're studying it at the beginning, then it's probably true. It won't change very much. It's not perfect, but it's doable. And that's the way we're going to do it next week. We start off with a blue dye. A blue dye, food coloring. And then our other component is the concentration of bleach, right? Sodium hypochlorite. We increase this value so high that we can ignore it. Well, we don't actually ignore it. What we do is we combine this concentration term into this constant, and now the rate becomes what we call a pseudo rate constant times A to the power. And the first time we run the experiment, we're going to find out what this value is, that K prime. And then we're going to do it again at a different concentration for bleach. So now we change the concentration of bleach, but it's still high enough that it doesn't affect the chemistry of A. And then we use we compare those two equations and determine what K prime is, and then back calculate to what K is. All right, there's a, let me see. Hold on just a second. I don't want to misspeak. So let me look at the method and be sure that all the information in there that I'm going to tell you about is there. Chemical kinetics. Here we go. All right. So this is what it looks like. And yeah, there's a discussion of there's a background discussion, and actually a lot of the stuff in here is what we just talked about. Then there's a discussion of the pseudo rate constant and how we deal with it, and then the method. And there's another document. There are a couple of other documents actually that you won't need right away. Here we go. All right. It's kind of hard to tell if this is in the frame because I lost my inset. But this talks about calculating the kinetic constant based upon this concept here. That document is in Brightspace, and I need to make a copy for here. This is just this is my spreadsheet. This is what I use to calculate your data when you give it to me. And we're eventually going to have to know what is the molar concentration of bleach. Okay, what's the molar concentration of bleach in both of those two exercises? You're going to do this kinetics experiment with the blue dye twice at different bleach concentrations. And this is where we calculate the concentration of the bleach. You have to know that. The concentration of the blue dye is related to its absorption in the spectrophotometer. So you'll watch it start off at a certain value and it'll decrease over time. And we're going to use those values, the absorbance values, to represent its concentration. We don't actually have to know exactly what the concentration is to complete the experiment. Okay. So let's get back to this thing. So when we let one of those factors increase concentration so that it doesn't change during the reaction, then in effect we're combining the concentration and its power of B into the K value. So we get a pseudo rate constant here. And that's only an initial step to get to where we're going. And a more complete discussion is given. There should be a discussion video in the lab section under the kinetics module that you might want to watch beforehand. Okay, this table just pulls everything together into one place. It's nothing special. What we're considering here, and let me see how we're doing on time and where we're at. Okay, we're doing pretty good. The point of this slide is to compare for a single set of initial concentrations and K values, what would be the effect after a certain amount of time, in this case 30 seconds, what would be the effect on the final concentration of A if the reaction were calculated as a zero rate law with that K value, or as a first order rate law with that K, or a second order rate law with that K. So we're going to do each one of these concentrations. There's the zero order. So if we say it's zero order, that means it has to be this value. And since we're incorporating a time factor, then we have to use the integrated rate law. So the K value here is 1 times 10 to the minus 2. There's your negative. There's the amount of time elapsed. And we calculate that A will be 4.7 molar after 30 seconds if it's zero order. If it's first order, then we use a different integrated rate law with the natural log, plug in the values, just like we did before. And now our calculation says it's 3.7 molar if it's first order equation. And then with second order equation, you probably have already figured out the concentration is going to be even lower. So now we use the inverse values with the same K value and the same time, and we find out that the concentration now is 2 molar. So the moral of this story is the order has an impact on the final concentration. As you increase the order of a reaction with the same K, you decrease the amount of final concentration for that reactant. Now, here's a discussion of method of initial rates. I think I'm going to have to erase this now because I'm going to need board space. Unless this is also animated in the slides, I'm not sure yet. Let me see if it's got an animation. Method of initial rates. Huh. Okay. I've got a different copy there in my, a different hard copy. I must not have printed this one out, so it'll be a surprise to me. Let me see what it's got. So here's an experiment where you have, and notice that the charges don't balance. The reason the charges don't balance is we've omitted the spectator ions. Like the manganate ion will have a cation associated with it. And maybe the protons, the H pluses, will have some other associated with them. So, and there might even be an anion in there. So those are eliminated because they're spectators. Right? So this is the net equation that we're interested in. And we've got 2 MnO4 minus plus 5 H2C204, which I think is oxalic acid, plus some other source of protons, an acid of some kind. Yields 2 manganese 2 ions, 10 carbon dioxides, and 8 waters. So that's our overall balanced equation for this study. What we do is we conduct separate rate experiments. And notice that we'll do the first one at these concentrations, molar concentrations for each one, right here, and determine the molar rate of the reaction as 2 times 10 to the minus 4th for the first one. For the second one, what have we done? We've actually held this term and that term constant, and we let this one vary. Okay, I'll show you what that means in just a minute. For the third one, let's see. For the third one, we hold this one constant here from here to here, and this one constant from here to here, and now this term is allowed to vary. And for the last one, we're holding this term constant, and we let the last one vary, be different. Okay, here's how this works. If we write the rate law, let me see if it's on the next slide. All right, so I'm going to have to do this one. So based on that information, the rate of the reaction, I'm not going to write the equation up here. The rate of the reaction is this term, the manganate, right, to the N, and times this one for H2C204, is it? Yes. And this one is to some other order, some power. And then we have this one to Mn. I hesitate to use O because it looks like that's an actual order value. Let's make it P. So each one of these has its own order, and then we have a K value for the whole thing. That's the rate law. Now, if we write this rate law for each one of those separate experiments, then we do them in pairs. Right? Let's do the second one first. Right? So the second one will be, we'll actually put the values in there that we know. So what's the rate for the second one is 8 times 10 to the minus 4. Okay. And then we have a K value. And then we have a value for MnO4, which is 2 times 10 to the minus 3 to its order. And then we have 1 times 10 to the minus 3 to its order. And then the last one is the protons, 1 to its order. Okay. So this is experiment 2. Experiment 1, and there's a reason I'm doing them backwards. Experiment 1 is a different rate. That's 2 times 10 to the minus 4. Okay. All right. This one has been allowed to change. 1 times 10 to the minus 3 to the n. This one stays the same. And this one stays the same. Okay. Now, why did I write them that way? Because I'm going to divide one equation by the other. I'm going to divide the top equation by the bottom equation. Okay. So what does that give us on this side? Well, it's actually 2 divided into 8, which is 4. Right? And the k here is the same k as there, it's gone. This one's the same as that one, it's gone. That one's the same as that one, that one's gone. So what we're left with is 2 divided by 1, or 2 to the n power. Right? If we've got this term in here, this term in here, and they're both the same power, then we can divide 2 times 10 to the minus 3 divided by 1 times 10 to the minus 3 is 2 to the n power. So what's n? N is equal to 2. Okay? So now we know that this value is 2. Okay? See what we're doing? That's why when we conduct these experiments, we adjust the concentration so that only one is allowed to change between 2 possible experiments. So that way, with 3 terms to work with to find out what their order is, with 3 terms, we need 4 experiments. And we do the same thing for each one of these others. Okay? I think this one turns out to be 1. Let's just do it. Okay, so if we change this here, right? We change that, and for the second one, we want the second term to vary. So now we want to use 2 and 3. Right? So we're going to use 3 on top and 2 on the bottom. And the reason I do that is so that this will be a whole number and not a fraction. So 1.6 times 10 to the minus third. 1.6 times 10 to the minus 3. And the other one is 8. 8 times 10 to the minus 4. And now these values are going to change. This is going to be what? 2? Yes. This will be 2 times 10 to the minus 3. Right? And this one's going to vary. And that one's going to stay the same. Right? It's still 1 and 1. But this one's going to be 2 times 10 minus 3. And this is going to be 1 times 10 minus 3. I believe. Yeah. Okay. So now these still cancel, those cancel, these cancel, and we're left with this one. So this one is 1 into 2 is 2 to the m power. Right? And this term over here, well, notice the difference here, minus 4 and minus 3. If we make this one minus 4, that makes this one 16. So 8 into 16 is 2, right? So 2 to what power is 2? M equals 1. So now we can say 1 is here. And now we have to do is the last one. All right. So let's see. This is going to stay the same. This one's going to be a 2. And this one's going to be 2 on top and 1 on the bottom. Okay. So this one's going to be the last one, which is the 4th experiment. And this one's going to be the 3rd experiment. So the 4th experiment is 1.6 times 10 to the minus 3. And this one's 1.6 times 10 to the minus 3. Correct? Yeah. This one's due to 1. This one's due to 2. Okay. So now the k's cancel. These 2 terms cancel. These 2 terms cancel. And now we have 2 to the p power, right? These 2. And this is 1. So 2 to what power equals 1? P equals 0. So the equation now is in zero order for hydrogen ions. Okay, so now we have our rate law, except we don't know what K is yet. So how do you find K? It's really very simple. Just take one of those experiments, plug in the values that you do know. Let's just take the first one. 2 times 10 to the minus 4 equals K. And under these conditions, this one is 1 times 10 to the minus 3, right, to the second power. And this is 1 times 10 to the minus 3 times 10 to the minus 3 to the first power. And that term is gone, right? Anything to the zero power is 1, right? So it doesn't matter. So if we solve this equation for K, I'm going to let them tell us what it is instead of having to stop and do the calculation. There is 2 times 10 to the 5th. All right. And you would just plug that value in here. 2 times 10 to the 5th. The rate is equal to 2 times 10 to the 5th times the manganate concentration. That should be a negative sign there. Squared to the second power, and oxalate to the first power, and this term is gone. That would be the rate law. It would just be those two terms because the other term doesn't matter. All right. So that's the method of initial rates. And there are a couple of examples in the review document. That'll give you some exercise your brain cells a little bit. Now we'll get to the topic of reaction mechanism. That is, what's happening inside that arrow? What's going on in there? Elementary steps in the reaction. Sometimes it'll seem like voodoo science. The premise is that we assume that most chemical reactions occur by a series of elementary steps, at least 2 steps. A few of them, I think, have been determined to be a single step. So, in effect, the overall reaction is an elementary step. But most reactions occur as 2 or more steps. And these steps may produce intermediate products. And you don't see them as final products in the overall reaction. So what that means is those intermediate products must be consumed in a subsequent reaction so that they don't show up in the final, in the overall reaction. Here's an example. NO2 plus CO yields NO plus CO2. So the blue balls are nitrogen, the red balls are oxygen, and the black balls are carbon. So we see in the first step, we've got 2 NO2s, right? Notice in the overall reaction, we've only got 1 NO2. So why do we have 2? Well, we'll deal with that as we go. But in the reaction mixture, you got lots of NO2s. I mean, you don't just have 1 NO2, you got lots of them. So 2 of them react, and they produce an NO3 as a product plus an NO. So what that means is we've got one of our products right here, NO, right there, right there. But this is an intermediate. So this intermediate now comes down to the second step, and it reacts with the carbon monoxide, right? And produces another NO2 plus the CO2. So there you have, we've used an extra NO2 here, but we got it back here. Right? So remember, when you have one reactant on one side and one on the other side with the same molar equivalence, the same amount, they cancel in the overall reaction. And that's what will happen if we add these elementary steps together. Then we should get, if they're accurate, if they're true, then we should get the overall reaction by summing the elementary steps. Now notice, before I do that, notice in this case, we have two molecules coming together, right, to produce some intermediates. Right? Whenever that happens, we're talking about a bimolecular step. We had one earlier where we decomposed a compound. That's unimolecular. There's only one reactant. Now that's assuming that the elementary step also includes a unimolecular, just one reactant. It's possible that that one also had multiple steps and interactions. So we're talking about this molecularity is describing an elementary step. So a unimolecular step just requires that the reactant, whatever it is all that's required. There's that one, and it decomposes, right? Changes. I suppose it's possible it could rearrange its molecular structure. A bimolecular step is where two molecules have to come together in order for a reaction to occur. And a termolecular step requires that three come together. Termolecular steps are very, very rare. We don't use them in elementary steps unless there's no other alternative. Because think about what the probability of getting three molecules to come together, exactly the correct orientation and exactly the right energies for the reaction to occur. It's almost impossible, very rare. Most reactions are either unimolecular or bimolecular in their elementary steps. So when we have two or more steps, they occur at different rates. Each one of those steps occurs at a different rate. The one that happens the slowest is the rate determining step. Now, all three of those, 3 or 4 or 5 or 6, however many steps, all of them can be happening very fast, in microseconds. But there's always one of them that's the slowpoke, and that's the rate determining step. So the overall rate of the reaction is determined by that one step. It's the weak link, so to speak. And if we know what that slow rate is, that's our starting point for deriving the rate law for that overall equation from the elementary steps. Okay, first requirement. Now, when a chemist proposes elementary steps for a reaction, usually does it based on some intuition, some experience. Or if it's a graduate student, his major professor is sort of guiding him in the right direction, him or her actually. But once you've got a set of elementary steps, and what they typically do is propose this set could be it, this set could be it, this set, they might have 1, 2, 3 dozen different possible scenarios of elementary steps, right? And then you go in and you start eliminating them. You eliminate the ones that are absolutely impossible. And then you go to the ones that are, very rare. They might have termolecular steps in them, so you kind of set those aside. And you whittle it down until you get to maybe 2 or 3 candidates. And in the middle of all this process, what you're asking yourself is, these proposed steps, can I add them up? Just like we were doing Hess's law for calorimetry. Can I add them up and end up with the overall equation for that reaction. If you can't, then that mechanism, that series of elementary steps has to be thrown out. They must equal the overall in order to be a valid mechanism. And once you've proposed a mechanism and its elementary steps, then you use those elementary steps to derive the rate law from them. And we'll do an example in a minute. And you derive the rate law from those elementary steps. And if it's not the same rate law as the one you determined experimentally, you throw it out. Right? They have to agree. All right. So here's an example. Dinitrogen pentoxide decomposes into nitrogen dioxide and oxygen. And these are the elementary steps that are proposed for that reaction. The first one is a fast step, where you get one molecule of N2O5 producing NO2 and NO3. Right? Notice NO3 is not in the overall reaction. So NO3 has to be used up somewhere, and it is in the second step. In the second step, the NO3 and the NO2 react again, and they produce NO plus O2 plus NO2. And then you get the NO in that second step, which is not in the overall reaction, and it reacts with another NO3 to produce two NO2s. Okay, those are the proposed steps. The first one is known as a fast equilibrium. That means it's occurring so fast in both directions that the forward rate is equal to the reverse rate. That's what we're saying. And then this is the slow step. So this is the rate determining step right here, this second step. And then the last step is fast. So really all we want to know is which one is the slow step. Okay, if you try to add those up now, are you going to get that overall equation? Notice that on the left-hand side, there's only one N2O5. Right? You need two in the overall equation, right? So we've got to manipulate these legally. I mean, we have to do it correctly and multiply the equations through by some factor in order to get the correct number coefficients for our reactants and products, and also cancel out those intermediates that should not be there in the final equation. So that's what we're doing with this one. That one's multiplied by 2 to give us two N2O5s. And that cancels two NO3s. Let's see. Yeah. 2 times this one makes two of these. That means this one and this one are both canceled because they're on opposite sides of the arrows. Okay. Now we can cancel the NO2s on both sides of this equation. We can cancel the NOs on this side of the equation. And then what does that leave us? Well, let's see. We got an oxygen over here. What are we going to do with the oxygen? Huh. Oh, I'm sorry. I was looking at the wrong place. There is an oxygen up here. There's one oxygen. There are four NO2s, so there's two here and two there. That's good. And there's two here. That's good. That's good. Okay. So when we add these three steps together, we get the overall equation. All right. This one's going to look kind of hairy, but stay with me. The overall reaction for this, the overall reaction is A plus 2B equals C. A plus 2B equals C. Okay, the proposed mechanism has A plus B in a fast equilibrium produces D. right? So there's an intermediate here that's not in the overall equation. And then that D reacts with, second step, reacts with another B, right? One of the B's react here, one of the B's react here, and yields C. So this one is slow. This one's fast. Okay. What's the rate law for this mechanism? If this is a correct two elementary step mechanism for that overall equation, then how do we get at the overall equation? Well, does it meet the first condition? This one's on the right, this one's on the left. They cancel. Here's an A, there's an A. There's a B, there's one of them. There's a B, there's the other one. And there's a C. Yes, we add them both together, we get the overall equation. First condition is met. Second step, what is the rate constant for each one? Well, this one's going in both directions. So we have a rate constant here for that equation, plus we have one in the opposite direction. That's what the -1 means. And then we have another one for this one. Okay? So now that we have those constants proposed for these mechanisms, we can write an expression for each equation. The slow step is the rate determining step. So we want to write that one first. Right? So what would be the rate for this one? All right, let's see if I got it animated here. All right. So the rate for this one is equal to that K2 times the concentration of D times the concentration of B. Notice in this case, the order for each one, because these are elementary steps, the order for each one is also the coefficient for each one. Okay, if there were a 2 here, we'd put power 2 here. Okay, this cannot be the final rate expression because we got a D in it, and there's no D in the overall. So we got to get rid of that D somehow. And here's how we do it. We go back to the fast equilibrium. The forward and the reverse rates are equal. So now we can say the forward rate of this one is equal to K1 times A to the first power times B to the first power. But that's also equal to K minus 1 times D. Okay, so those rates are equal. That's why we write it that way. Now we want to solve this equation here for D so we can plug it in here, because if we solve it for D, then everything that's not D is on this side and it goes in here and we got rid of D. Right? So if we solve for D, concentration of D, that's equal to K1 over K minus 1 times A times B. Like that. So now we substitute this right in there. That should be on the next slide. There we go. So now if we do that, we have a new rate expression where we have K2, and then whatever is inside D, which is K1 over K minus 1 times A times B, and then we have B on the outside here. So we just substituted all that right in here. So what do we got? Well, we can factor out these constants. Right? If they truly are constants, then we combine all of these constants into a single rate constant right here. And then that leaves us with A to the first power and B to the second power. Okay? So that's our rate law for this equation. Now, coincidentally, the order of A is first order, and the order of B is second order, right? Don't take that to be gospel, because that's not supposed to, the overall equation you can't use that value for the order of B. It just coincidentally turned out that way. All right. So we've been talking about the reaction kinetics in terms of laws, right? This is what happens. We don't know why, it just happens that way. And we've sort of been sliding into theory, talking about these mechanisms. And we introduced the concept that we're going to discuss now when we were talking about the unimolecular, the bimolecular, the termolecular type of elementary steps. And the reason that they're important is based upon this model, the collision model. In other words, what we're saying is that in order for a reaction to occur, two or more reactants must collide. They have to make contact. And when they do, when they make contact, this reactant collides with B, right? And something happens. Okay. First of all, first condition, once they collide, is that there has to be enough energy. Activation energy. There must be enough energy to break the bonds that may be in either one of these, because this might be a molecule. Any of the bonds that are in there must be broken, and new bonds have to start forming. And this typically is related to temperature. Okay? Higher temperature means more kinetic energy. And then the other thing that has to happen is the molecules must be oriented properly. Right? If the reaction site during the collision is on this side of the molecule here and on this side of the molecule here, and they come together like that, nothing will happen, no matter how much energy they have. So they have to be oriented correctly with enough energy to break bonds and form new ones. Go through an intermediate step, an intermediate stage. Those are the basic premises of the collision model. And whenever we say model, we're talking about theory. Right? So there's a theory behind this that supports the model. So what do we mean by activation energy? Well, this graphical representation helps. That's kind of a small picture. So this is reaction progress. So it's roughly equivalent to a time scale. And this is energy. Energy of all the reactants, all the products, and anything in between. Okay, so if we start off with reactants here, and we heat them up where they get enough energy there. At this point, they're in a transition state. So this side is reactants. This side is transition. Sometimes it's called an activated complex. Transition state. If you have that much energy plus just a smidge more, then you're going to come over this side and go down to products. Okay? The amount of energy, the activation energy, is the difference between here and there. That's how much energy is required. Notice also that if you start off at this energy and you end up at this energy, what change has occurred? It's a negative change. You had more energy to begin with than you did when you ended. And that, in terms of thermochemistry, is an exothermic reaction. You've given up energy, right? So whenever you see this higher than that, it's exothermic. If we were to go backwards, right, we'd need that much energy to go backwards. You need more energy to go the other direction. The endothermic reaction would be higher activation energy. Okay. This is just restating the collision model steps. Now, there was a pretty smart fellow, his name was Svante Arrhenius, and he was doing experiments with conductivity in solution. And in the process, he proposed this equation to relate activation energies to the rate constant K. So there's the K, the first term is K, and you see in the power of E, and this is the same E as the natural log uses as a base. That's their relationship. A is a factor that's got several other things combined. And then R is the gas constant with the energy term, so it's 8.3145, and not the other one with liter atmospheres, 0.08206. That's different problem solving there. This gas constant is in terms of joules per K, that is temperature, K moles. And then temperature is in units of K. Okay. So this is a true equation, you know, and if you can determine what A is, and you can determine for a temperature what the rate constant is, you can calculate the activation energy. Or it's like any other equation. If you have all the factors covered, all the variables have values except for one, you can solve for it. But it's difficult to find out what A is with this equation. So we need a modified version. And that's where we go to this version. This is similar to the integrated rate law. And it's rearranged in such a form that it represents a straight line. Right? So this log K is equal to a negative activation energy divided by R, and then the inverse of the temperature in Kelvin, plus the natural log of the concentration of the value of A, that constant in there that we couldn't get a hold of. So this is your Y, this is your slope, this is X, and this is your Y-intercept. So if you conduct the experiment at least 2 times, 3 or 4 is better, at different temperatures. And for each temperature, you determine the rate constant. And then you plot that line. So you plot the log of your K values, your rate constants, against the inverse of temperature in K, right, K to the -1. And you plot those, then you get a negative slope, and that slope is e to the A over R. Well, that's negative e to the A over R. We know what R is. So if once you got that value, the slope of the line, you can solve for the activation energy and determine what the activation energy is for that reaction. All right, here's an example. Right. So in this case, the slope of the line is -1.2 times 10 to the 4th. And then we set 1.2 times 10 to the -4th equal to that value, right? It's a negative number, so a negative number equals a negative there, so the negatives go away. and then you take R, multiply it times that number, and that's your E to A sub A. Oops. Oh, okay. All right, it's already 4 o'clock. Let me see how much more I have to go. A little bit, not too much. Let's see. Okay. This is I created this one myself. This is a proposal. When I was a student, many years ago, there was a rule of thumb. In fact, I was introduced to it first in biology class. And what it said was, for every 10-degree increase, the rate of reaction doubles. So for every 10-degree C increase, you get a doubling of the reaction rate. Now that's a rule of thumb, right? It will vary, right? Depending upon the reaction and the activation energy that's associated with that reaction. So what I wanted to do now is say, okay, if that rule is true, what does the activation energy have to be for this rule of thumb to be exactly correct? For the reaction rate to double for every 10-degree, what is the activation energy? Now, I had to pick a couple of temperatures that were reasonable. So I picked 25 degrees and 35 degrees. So in order to use the linear version of Arrhenius equation, I need to have a temperature spread, like 2 temperatures. So this is the next slides will have the calculations. Notice that the first one on the upper left, what we're doing is we're calculating the K temperature for 25, and then we're calculating the K temperature for 35. And then the Arrhenius equation here is this one. That's the K for this temperature, right? And if we're going to say that the rate doubles, then the K has to double also. So this is the K for the lower temperature. This is the K for the higher temperature. And the second K is equal to 2 times the first K. If the rate's going to double, then the K has to double. So the ratio of these two, K2 to K1, is actually 2 over K1 divided by K1. So that value, that term is 2. But the equivalent of 2K1 is this one here. So we plug that one in here, and the ratio to that one here. So notice that what we have here is the A's are the same, the activation energies are the same, R's are the same, and we have the 2 different temperatures. So we reduce this equation to what is it, the power of E then? Since this power is here of E and this power of E, then E to the numerator power minus the denominator power. And notice the denominator power starts with a negative, but we subtract it, so now it's a positive. Oops, sorry. So that gives us, this expression is the power of E. And now we factor out 1 over T. And that leaves us with minus E sub A over R times the 1 over T2 minus 1 over T1. Right, then we go to the next slide. So what are we going to do here? Well, the easiest way to get around this one is to take the natural log of both sides. If we take the natural log of both sides, then the natural log of E to a power is just the power. So that's what we've done for the next slide. The natural log of 2, and I moved the R over here. Notice the R was here, and if we get rid of this E by taking the natural log of both sides, then I take that R and put it on the other side. So that's what we've done here. The natural log of 2 times R equals minus E sub A times this. Okay, so we rearrange it so that we get E sub A on one side, and then we plug in our values. All right, so we plug in our values for the temperature and solve it. And as it turns out, for this rule to hold exactly, for every 10 degrees, we exactly double the rate of reaction. The activation energy for that reaction has to be 52.9 kilojoules. That's the only one that fits this exactly, right? If it's higher than that, then you get a higher increase in rate. If it's lower than that, you get a lower increase in rate. All right. So our final discussion is on the topic of catalysis. What is a catalyst? The definition of a catalyst is simply a reactant that enters a reaction one end and overall comes out the other end apparently unchanged. And it causes an increase in the reaction rate. Now, how does it do that? Actually, what happens is when you introduce a catalyst, you are changing the structure of the elementary steps of the reaction. So if we're saying, let's see, we've got a reaction where hydrogen peroxide decomposes into oxygen and water. That's not balanced. Let's see. H2, let's see. Let's say we have 2 there and 2 here. That'd be 4 hydrogens. That would be 4. That'd be 2 and 2. Okay. So I have 2 oxygens there, 2 oxygens here. Right. 4 oxygens, 4 oxygens, 4 hydrogens. There we go. That's balanced. That's the overall equation for the decomposition of hydrogen peroxide. And it has certain mechanism steps that occur in here, right? If we introduce a catalyst, the iodide ion as potassium iodide, then the elementary steps will change. And the elementary steps will change such that the slowest elementary step in this new mechanism is a lot faster than the slowest step in the uncatalyzed reaction. It speeds up the reaction. Okay, it offers a different pathway of elementary steps for the reaction. That's what a catalyst does. Now, if we look at it in terms of an energy diagram, what we see is that for the uncatalyzed reaction, you have an activation energy way up here, but a catalyzed reaction, the activation energy is reduced down to here. So what the steps, the change in the elementary steps does is offer a lower activation energy required for that slow step. This is another way of looking at catalyzed versus an uncatalyzed reaction. The one on the left, the plate on the left, shows the number of collisions with a given energy, right? And this is the same curve on both charts, exactly the same. So that means they're at the same temperature. And you have the same spread of energies for all of the reactants. Okay. So the energy increases from left to right. Most of the reactants have energies in here, but a few of them have pretty high energy, and they have enough energy to meet or exceed the activation energy required for the reaction. The uncatalyzed reaction activation energy is here. So we have this many collisions that satisfy the condition for the activation energy uncatalyzed. If we introduce a catalyst, now the number of collisions that produce a reaction has increased because we take the activation energy and move it to the left, and that encompasses more collisions. So the reaction rate increases. And when we talk about catalysts, we can subdivide them into two categories. The heterogeneous catalyst is one where the catalyst is a different phase than the reactants. So, for instance, in the exhaust of your engine, most modern cars have a catalytic converter, and the reactants blowing through that catalytic converter are all gases. What we want to do is take the incomplete combustion products of the internal combustion engine, and with the catalyst, cause those reactants to complete their reaction. So that's what the catalyst does. Only inside the catalytic converter, the catalyst is a solid. It's actually a matrix, a ceramic matrix that's coated with platinum and palladium. They act as the catalyst. So they're different phases, right? The catalyst is a solid, the reactants are all gases. That's a heterogeneous catalyst. And they undergo a process called adsorption, not absorption. If you put a paper towel into a glass of water, watch the water move up, that's absorption. Adsorption is a surface phenomenon where molecules are momentarily attached to the surface of some material. It could be the catalyst, or in my previous life, it could be reactants that are attached to the roots, small rootlets of plants. Or it could be, they could attach as the water moves nutrients down through the soil profile, they could momentarily be attached to the surface of soil particles. That's adsorption. Oops. So this is a proposed mechanism for a heterogeneous catalyst. What happens is the reactants are adsorbed to the surface, and the activation occurs at that site. They become, they're hot, of course, there's a lot of energy there. And then they are oriented properly towards each other because they can migrate across the surface of the catalyst. And when they meet with the proper energy, they're oriented properly, they react. And then the products that are formed are then desorbed from the surface. And in your car exhaust, then they're blown on out your tailpipe. This is an artist's idea of what happens in a catalytic converter. You have oxides of nitrogen, you have unburned hydrocarbons, and you have carbon monoxide. And they go in here with the catalyst, they come out as carbon dioxide, water, and nitrogen gas. Now, when catalytic converters were first being used, I think back in the 70s was when the environmentalists started feeling their oats, and they got the EPA to impose restrictions on internal combustion engines. So they introduced catalytic converters into the exhaust systems of new cars. Those new cars had exhaust systems with little beads, little ceramic beads in them, right? And you could, if you pulled your catalytic converter off, you could shake it and hear those beads rattle. So some smart mechanic decided, well, listen, this catalytic converter is causing back pressure on my engine and decreasing the horsepower. So what if I go in there and just take my screwdriver and poke a hole in the bottom of it? All those beads come flowing out. Each one of those beads is coated with a very thin layer of platinum and palladium. So that's the reaction site. The ceramic bead is just a support matrix. So they do that, and then they clean it up so you couldn't see the hole, or they poke a hole where an inspector couldn't see it. And the only way you could tell that it didn't have a functioning catalytic converter was to do an exhaust check. Right? So that's what they started doing. And in fact, I'm from Georgia, and at some point in time, Georgia law changed so that you didn't have to have a safety inspection of your vehicle, but you did have to go for an exhaust check. So they would catch people that had messed with their catalytic converters. Okay, so the manufacturers came up with another idea. We're just going to make the ceramic matrix a porous solid. So gases can flow through it, and then we'll coat the matrix with the noble metals. And from that point on, the only way that you could get the catalytic converter out of there was to saw it in half and pull the plug out. Okay, that's a heterogeneous catalyst. A homogeneous catalyst is one that functions the same way as a heterogeneous catalyst, only now the catalyst is in the same phase as the reactants. So if the reactants are all gases, then the catalyst is a gas. If the reactants are all liquids, then the catalyst is a liquid. And I erased it now, but that decomposition of hydrogen peroxide can be accomplished by dissolving potassium iodide in water and then pouring it into the hydrogen peroxide. And then the reaction happens so fast, and if you have a little soap in there, a little food coloring, it'll bubble up like a big smoke chimney. But those are homogeneous catalysts. They're in the same phase as the reactant molecules. Nature's catalysts, the cellular catalysts, are enzymes. Now, there's a difference between enzymes and inorganic catalysts, like this potassium iodide. Or in the Haber-Bosch process, the catalyst was finely divided iron particles. The inorganic catalysts allow the reaction rate to occur fast in both directions. Enzymes are slightly different. Most enzymes, not all, but most enzymes are constructed in such a way that they only catalyze in one direction. So if you want the reverse reaction to occur, you need two different enzymes, one for that direction, the forward direction, and one for the reverse. That does one very good thing for a cell. It allows for control. You control the reactions and the directions that they go. And enzymes can be inactive. They can be in the cell matrix. And if the cell needs an enzyme really quick, it just sends the activation signal in some form or fashion. The enzyme activates and the reaction goes. So there's more control with enzymes than there is with inorganic catalysts. Much more control. Oh, here we go. Let's watch this.
Try yours. So that's the technique. Just dump it right in and see what happens.
Oh wow. Okay.
Okay. So
Whoa.
we're releasing
Okay.
lots and lots of oxygen gas. Okay. So why don't you go ahead and do yours now? Yours is a little bit different container. It's got just dump it in really quick.
Okay.
Perfect. Yours is like more. And you just generate tons and tons of oxygen. It's being trapped by the soap. Okay. It's like a supersized version of what kind of happens when you pour it on your body.
Sure.
Where that catalase enzyme breaks it down.
But again, we're not actually cleaning anything, if you will.
Technically, the hydrogen peroxide, when it generates this oxygen, can kind of dislodge big hunks of stuff. This is like more of
So that decomposition of hydrogen peroxide, when they poured that liquid in there, which was a solution of potassium iodide, the iodine is the catalyst, and it caused the decomposition of hydrogen peroxide 1,000 times faster than it would in nature. Now, for this thing to really work well, you can't use, it's not efficient to use 3% hydrogen peroxide off of your medicine shelf. This works a whole lot better if you use 30% or better hydrogen peroxide. And you have a little dish soap in there to make the bubbles and some color. Okay. This is a proposed mechanism for that decomposition with iodine as the catalyst. Notice that iodine enters This is the slow step where iodine associates itself with, it reacts with the hydrogen peroxide and produces this intermediate plus this intermediate, and then you get subsequent steps, and then you end up with oxygen gas at the end. Now we have to add all these together, and if we do, we end up with an overall reaction that eliminates the iodide. Notice the iodine here is on the left-hand side of the arrow, iodine here is on the right-hand side. So that's a dead giveaway that this is a catalyst. It comes in one end, goes out the other, supposedly unchanged. So it would not be part of the reaction equation. Sometimes we put it like an iodine on top of an arrow to show that we did use it to do that. Another interesting form of catalyst action is in the upper atmosphere, where we have ozone, right? What happens is in the upper layers of the atmosphere, oxygen molecules are exposed to ultraviolet radiation from the sun, and it causes a reaction of oxygen to form ozone. So that forms in the upper atmosphere. The advantage to ozone in the upper atmosphere is this is very efficient at absorbing ultraviolet radiation, much more efficient than oxygen gas itself. So that protects the lower layers of the atmosphere and any plant and animal life down there from getting too much ultraviolet radiation. Well, there are certain chemicals that are, most of them man-made, that are released into the atmosphere that catalyze the decomposition of ozone, and this is one of them. Nitrogen oxide, nitrogen monoxide will react with oxygen, and the end result is it will produce, this is the overall reaction, it will produce oxygen instead of ozone. So that's not the only one that gives us trouble in the upper atmosphere. The other one was initially freon. It was this type of freon, which was, I think they called it freon 12. But the chemical structure of it was, you had a carbon here, and you had maybe a fluorine here, and a fluorine here, and a chlorine there, and a chlorine there. So this refrigerant, this freon 12, was very efficient at catalyzing the decomposition of ozone. As it drifted into the upper atmosphere, ultraviolet light caused a reaction which produced these two products. And this is the important one right here. This single atom of chlorine, if you remember your Lewis dot structures, that chlorine in the valence electrons has one unpaired electron. That unpaired electron is extremely reactive. This is called any chemical, any molecule, any atom that has an unpaired electron is called a free radical. Now, some of them are neutral, like this one, right? No charge. Some of them have charges, right? And you may hear in the popular literature or on the news reports about free radicals damaging your body. In chemical reactions in our body, day after day after day, our bodies produce free radicals. And we need some mechanism to scavenge those free radicals before they can damage any of our, especially damage our DNA. So get back to the topic. These chlorine free radicals react as catalysts with ozone to decompose it and make oxygen gas, and then they're released again to go decompose another ozone. So that's why freon was banned. And now we use other types of hydrofluorocarbons in our refrigerants that are less susceptible to that decomposition producing free radicals. Right? They're more expensive, of course, but they don't do as much damage to the ozone layer. Okay, that's it.